So now we're going to bring math. So we have logic, we had programming. Now we're going to bring the mathematics into our little triangle of love. So we're going to start adding data structures here, and we're just going to define data structures as new rules for our language here. So this is the Boolean data type. We're going to add two introduction rules. One called T, which should make you think of truth, and one called F, which you might think of as the false Boolean. Note, like this is totally different from the logical truth and falsity, right? It's just a type of two elements which we've labeled T and F, and it's up to you to interpret that however you want. But it has no logical relation like our top and bottom symbols for true and false that we used earlier. Dueling will need elimination rules. So if you have some arbitrary Boolean B, and you have two arbitrary proof objects of C, you can put them together. So this, we've left the realm of logic here, right? So you can put them together to get this elimination rule: if B, then P, else Q. And this is really stupid from a logical point of view, because if you could prove C twice even, right, you could just have C, right? It's okay. But this produces a new C that is potentially different from the C's that you provided as input. But we'll make this more interesting a little bit later. But from a computation point of view, this is totally a legit thing to do. And in fact, we're going to give two very nice reduction rules, which says that if T, then P else Q, that reduces to P. And if F, then P else Q, we'll have that reduced to Q. Right? So this is just your standard if statement. We can play the same game with the natural numbers. We're going to say that 0 is a natural number, just from nothing. And this is a little bit more interesting. If you have a natural number n, then S of n, where S you're supposed to think successor. So if you have any natural number n, there's another natural number n, which is its successor. And its elimination rule, again, a little bit silly from a logical perspective, but from a computational perspective, it'll make sense. If you have some natural number n, and you have P of C, think base case, P of C, and from any number, any free variable natural number n, and R, think recursive result, C, you can derive Q. Then we have this recursive elimination expression that puts them all together through C. And again, like we just proved C, from a logic sense, it makes no sense because we have a proof of C over here. Why do we need to make a more complicated proof of C over here? But from a computation point of view, it's totally legit again, right? We're going to have our we're going to call this primitive recursion. Primitive recursion of like when it's given 0. It just reduces to the P, which is our base case. And if we apply it to the successor of some natural number, it's actually a little bit complicated. We'll return Q, and we'll fill in the holes. For M, we'll fill it with N, which is this value over here, which is a predecessor of the number that was applied to it, right? Because this is a successor of N, so N is the predecessor of this input over here to recursion. And then we replace R with another call to recur to rec, except this time it's rec n instead of rec sn, so we're looping on a smaller index over here, and then everything, the body is the same. And so this basically will expand out again and again and again, making more and more copies until the counter reaches 0, in which case we'll terminate with a P over here. So it takes stacks of these Qs, and puts a bunch of Q's together and puts a P on top. And so we can define addition using this recursion operator. X plus Y we just defined to be rec x and so we have to give a base case. So in case in case x is 0, we'll just return Y. And if we're in the successor of something, then we'll return the successor of the sum of the thing. Basically, we'll do recursion on 1 less than the x input, get the value out, and add 1 back in. And if you run it a couple times, you'll see that this is in fact defines addition. So only structural recursion is allowed. Again, all functions terminate. Our language is not Turing complete. So you think this is very unfortunate. How could I possibly use a not Turing complete language? But really, honestly, it's not so bad. Like the Ackermann function, which is this, like depending on whether you're a logician or from a computer programmer's perspective, the Ackermann function is an insanely fast-growing function, right? So you will like you will never want to compute. You never want your algorithm to take longer than the Ackermann function because it makes exponential functions look quick, right? And that's that's easy, right? We can go much longer running algorithms than that if you like really so desire. But there is a limit to how much recursion you can. Next up is doing inductive proofs.